And in this video, I'd like to give an introductory level talk on finite automata. So I'd like to divide the talk into three parts. First, let's talk about what a finite automata is, and let's see a representation of the finite automata in the second section, and finally, let's end it with a formal definition of finite automata. So what is a finite automata? Well, to put it in simple words, finite automata is just a model of a computer. The unique thing about a finite automata, which sets it apart from other models of computers that you might have seen so far, is that you have a very restricted amount of memory in a finite automata. So why would you need a machine with such restricted amount of memory? Well, you'd actually be surprised with the amount of finite automata you come in contact with on a daily basis. A very good example of a finite automata would be a coffee machine. So within a coffee machine, we have a fixed states. So once you on the machine, it asks you to pour water, and then it asks you to place a coffee packet, and then finally it brews. So this restricted amount of memory still gives you a lot of performance and a lot of applications that you can have. So let's see a representation of a finite automata. Finite automata is also called a state transition machine. This is because at any given point, a finite automata can only be in a unique state, and it transitions between different states based on the input that you get. So for the sake of argument, let's keep it simple and let's define a finite automata which just gives me an accept or a rejection. So the output would be either accept or reject. So let's say my finite automata has 4 states. Let's say Q1, Q2, Q3, Q4. And just to keep things simple, let's think of the input that is given to the finite automata as ones and zeros. Basically a binary language. So now, let's say the machine starts at a Q1 state, and let's say if the machine at the end of an input is in the Q2 state, it accepts the input. If not, it rejects the input. So let's see the transition that can happen between the various states. So let's say on reading a 1, it goes to Q1, on reading a 0, it goes to Q4. For Q2, on reading a 1, it stays at Q2, on reading a 0, it goes to Q4. For Q3, on reading a 0, it goes to Q4, on reading a 1, it goes to Q2. For Q4, on reading a 0, it goes to Q4 itself, on reading a 1, it goes to Q2. So yeah, this would give a representation of a 4-state finite automata with the input language as a binary and then an output as a yes or a no. So now let's end this with a formal definition of what a finite automata would be. So from this example, we can find out what all we need to describe a finite automata. Like I showed, you need various states to describe what all states the finite automata can have. So first of all, we need set of all the states. Next, we would need a state which describes us where the automata starts from. So we need a start state. Next, a finite automata can have 0 or 1 or multiple accept states. So we need a set of states which describes the accept state, which would say whether the input string is valid or not. So we need a set of accept states. And next, in this example, I've given binary inputs, but at the same time, I could have given any other language that the finite automata could have transitioned from one state to another. So we need a language which describes that is read by the finite automata. So you need a language, and then you need a function that describes, like let's say if I'm on a state I, and if I read a alphabet A, it would transition to another state J. So similarly over here, you're on Q1, you read 1, you go to Q2. So you need a transition function which shows you how you transition between different state of finite automata. So these are the 5 things that uniquely define a finite automata. Thank you.